Ladies and gentlemen, children of all ages, it's time to take our vector multiplication one step further and introduce the cross product. I know you always told me that I start my lectures by clearing my throat and saying so, and so I needed to come up with something else to do. That was it. I hope you don't mind. Well, before we get into the cross product, we'll write at the top of the piece of paper, cross product. Okay, well, what about it? Before we do that, we're going to do a quick review of our multiplying vectors. And what is it about multiplying vectors that we have done so far? Well, we looked at the dot product. And it's always good to do a little quick review. The dot product is also called the scalar product. And how does it work? It equals, or defined as, I'll say, u dot v equals u1 v1 plus u2 v2 plus u3 v3. Just like that. And that gives us a scalar quantity, right? Because these are just scalars, u1, v1 scalar, u2, v2 scalar, u3, v3 scalar. Add those all up, still a scalar. And trigonometrically, what does that work out to be? Works out to be the magnitude of u times the magnitude of v times the cosine of the angle between them. And what does that look like? If we have a vector like that and then some other vector like that, I didn't mean for that to be angled like that, but it'll still work. And I called that u, and I called that v, like that. The dot product winds up being, do it in orange here, the magnitude of it at least becomes this thing here, this distance, the magnitude of component of u in v direction, right? Or it could go, or the magnitude of v in the u direction. That works too. All right, so that's what the dot product is. Comparing that now to our new topic for the day, the cross product. What does that work out to be? We write that as u cross v, like that. And I'll do the geometric, just like we did a geometric interpretation of this. We'll do a little geometric interpretation. Come back here. Geometric interpretation of the two here. So if I had u and I had v here, the cross product winds up being the area of this parallelogram. Like that. And we know that A, the area of, well, this is a parallelogram in this case, equals the base times the height. Well, the height really, I can draw, we're getting really multicolored, kind of like this. If that's the height there, and that's theta, make that a little better, theta. So equals v is the base, and the height is u cosine theta. So the magnitude of u times, oh, the sine of theta, excuse me. the sine of theta. So it's v, magnitude of v times the magnitude of u times the sine of theta, which gives us the area in this blue triangle. But wait, what's wrong with this? Another name for the cross product, I'll give you a hint, is the vector product, right? We have a dot product, which is a scalar product. Cross product is a vector product. Scalar, scalar, scalar. This is a scalar. This is scalar. Wow, my handwriting is rough today. I apologize for that. So we need add some direction for that. So we'll add in a little trick here. We'll say that the u cross v equals the magnitude of u times the magnitude of v times the sine of the angle between them. But that whole thing gets multiplied. This is still a scalar times a special little vector called n hat. Okay, so n hat, this is Dressler notation. Hat, of course, means unit vector, but n is in fact a vector and it stands for normal. What does normal mean? Let's make a little note here that n stands for normal unit vector. Normal unit vector, like that. And what that is, n hat is orthogonal to u and v. It's orthogonal to both. So the question is, how many are there? So I had a nice little drawing ready to go, but it's not going to fit on this page, so I'll do it over here. So how many normal vectors possible? Well, how many unit vectors are possible? Let's draw a little coordinate system down here. We'll call that some axis there, and we'll draw another axis there, and another axis there. Make this one a little bigger. So if I put my u vector down this way, we'll do it in, I'm going to get multicolored here again. If I make my u vector here, so right along with the x-axis, and just for kicks I'm going to make this x. I'm going to make this y. I'm going to make this one z. So if I make my u along that axis there, and I make my y along that axis there, or my v goes there, so my u cross v, right, this normal vector has to be perpendicular to both, so it has to be perpendicular to this plane, which means my n hat must go this way. I could draw it, I could draw an n vector that way, that's option A, or I could draw another option, I could have an n vector that way. All right, so I've got two options. However, this could be much longer. I could have a lot of normal vectors. I could be very long, it could be very short, it could go this way, this way. So how many normal vectors possible? There's an infinite number. Infinite number. But if I said how many unit, so how many unit normal vectors are possible? Well, that becomes a little easier because now it has to go either up or down, and they have to be unit vectors, so it can only be one long. So that means there's only one up or one down, and that means there are two. Now, and then this is terrible notes. How many normal vectors possible? Infinity. How many unit normal vectors possible? 2. And finally, how many, let's call it right-handed unit normal vectors are possible. Right? Now, what does right-handed mean? Right-handed means if I go u cross v, so if I'm going u cross v like this, that means if I take my right hand and I have my right fingers go in this direction, so my right fingers are pointing this way and I kind of make a fist, my thumb points up. That means it's right-handed. So this becomes the unit vector for, this becomes the right-handed unit vector that way. If I wanted to go the other way, if I wanted to do v cross u, and this would be kind of a wrist buster of a move here, if I try to go this way, so v cross u, my right finger is going this direction. If you imagine that, put your hand out by the screen, your thumb will point down. So that will be n hat that way as well. Alright, so the right hand rule, and this is very hard to draw here, but we'll just label that it's very important, that it's right hand rule for n hat. Right. So why are we doing this right-handed rule stuff again? Let's go back to make sure we understand. This is just a scalar, u cross v. It's the magnitude of u times the magnitude of v times the sine of theta. This is all a scalar. I need to multiply it, this scalar, by some direction, which is the unit normal vector, the normal unit vector, which is orthogonal to both and follows this right-handed rule. So if I go u cross v, it goes up. If I go v cross u, my fingers go this way, my right thumb goes down like this, and it becomes this way. Let's investigate that just a little bit further. I'm going to draw another coordinate system over here. And we're going to label it the same way we just did, with this going across like that, and this coming across like that. And once again, I'm going to call this X, I'm going to call this one Y, and I'm going to call this one Z. Does that work? Is that a right-handed coordinate system? Sure it is. So it's thumb, index finger. It's a real wrist buster to go thumb, index finger, Z, pointer finger, or middle finger, that way. So it's a right-handed coordinate system, but I'm going to draw in these three very special unit vectors that we already have. So that will be the unit vector that goes in the direction of the x-axis, one unit, is going to be I hat, and the one that goes in the direction of the y-coordinate is, what is that one again? J hat, and the one that goes straight up is k hat. I hat, j hat, k hat, those are the three unit vectors we talked about the other day when we first introduced vectors. So let's quickly take a look at I cross j. So I hat cross j hat would equal, well, it's the magnitude of I hat times the magnitude of j hat times the sine of the angle between them, and then I have to multiply that by the unit vector that's orthogonal to both, and it has to follow the right-hand rule. So I hat j, so if my right fingers go from I pointing, curling over towards j, then my right thumb would point up along k, so my unit vector really here is k, right, because that's a unit vector and it's perpendicular to both. The magnitude of I is 1, the magnitude of j is 1. The sine of, well, what's the distance between the theta between I and j? Well, that's 90. The sine of that, oh, conveniently 1. So we can see that I cross j gives us k. Okay. And then, so if we make a little table down here, I cross j equals k. Now, what if we did j cross k? J cross k, right-hand rule, our right fingers go from j up here to k, and then our right thumb would stick out in the direction of I. So j cross k, and that will give me the unit vector I. And finally, what's I cross j, j cross k, what do we have left? K cross I. Alright, so k cross I, that's kind of another wrist buster here, but if our right fingers point that way, k to I, curling this way, then my thumb points in the direction of j, so that means k cross I. K cross I must equal j. Alright, good. Now, an interesting thing comes up if we switch this. What happens if we switch and we go, instead of I cross j, we go j cross I? So this time our right fingers go this direction, from j to I, which means our thumb points down. Now that's interesting. That j cross I points in the opposite direction. So that makes it negative k. Interesting. Likewise, if I went k cross j, so my right fingers go this way, k cross j, well, that means my right thumb would point in the negative I direction, like that. And then we can assume that if we mix the order here, I cross k, that it'll probably equal negative j. Let's check that to be sure. I cross k, here's I, k, our right fingers go like this, and sure enough, our right thumb points back this way, and that'll be negative j. All right, that checks out. Now, there's a little circle here that a lot of people make. I don't know how many of you listening or watching are musicians, but in music we have this thing called the circle of fourths and circle of fifths, I think it's called. Now, a little biography, both my parents are music teachers, and every year or so I say, Mom, and I'm 40 years old, right? So I'm still calling my mom for music advice. Mom, how does the circle of fourths work? And she explains it to me, and I still don't get it, and somehow tells you the number of sharps and flats, but I don't get it. So we make a little plus in here like this. So I cross j gives you k, j cross k gives you I, k cross I gives you j, and if you go the opposite direction, everything becomes negative. Right? So instead of the circle of fifths, we'll call it the circle of unit vectors. In fact, I'm going to label it that. Circle of unit vectors. And I'm going to put a little box around that because I never really understand the circle of fifths and circle of fourths. But at least I understand this. So at least I have one circle that I know. Alright, so this is how we cross this basis, the Cartesian normal unit vectors. I, j, and k make a unit normal basis. One more thing that's kind of interesting about how this works, if we ask ourselves, how do we maximize cross product? Well, remember that the cross product kind of gives us the area in the parallelogram. So if I have two vectors that are at a pretty small angle relative to each other, like this, u and v, you know, that doesn't make a terribly big parallelogram. Kind of goes like that. So you know, it's all right, but it's not the biggest one you might be able to get. I could increase the angle a little bit between u and V, so this is V down here. If I increase that angle some, you know, I use the same length vectors, all of a sudden I get a little bit bigger, you know, parallelogram here. Because my base is the same, but my height has increased. So that's a little bigger. Well, how do I maximize it? What if I made them perfectly perpendicular to each other? And what if I made them straight? But I can't. So that's as big as it gets. So this becomes the max when theta, the angle between them, is 90 degrees. Theta equals 90. So that means sine of theta equals 1. So then U cross V maximize. Maximum. I can fit that there. Why do I care when it's a maximum? Well, here is a picture that I will surely mangle, but I'm going to try. I can draw it pretty well on real paper, but drawing on the computer is tough. Some of you might recognize this. That thing there, and we'll put a little circle in there. What is this? This is a 3/4 inch nut, right? And what do we do with the 3/4 inch nut? Well, we put a wrench on it. So I put a wrench like that. Make a little bigger spot there for the combination end of it. It's a pretty wimpy wrench, but we go like that, go like that, go like that, go like that. So here we have a wrench. Here's a nut. Now, when I want to rotate this thing, if I want to rotate, wow, this is a terrible wrench. But if I want to rotate this thing, what do I have to do? I put some force on it. Now, when I put the force on it, let's just say my force doesn't work exactly the way it's supposed to, and I put some force on it like this. Right? Just for kicks. So I'm going to call, well, let's label some more vectors here. In fact, I'm going to label, where am I looking here? The torque equals force cross. Now, I get this backwards sometimes because I spend too much time doing it as a scalar. It's R cross F. So this angle, this blue vector here, I'm going to draw the length of the wrench. And just for phonetic spelling, I'll call that R for wrench. And then the green one I will call F for force. So I could try to draw a parallelogram here, but I'm going to apply kind of a clever little trick. And I'm going to resolve F into two components. This is going to be F, we'll call it perpendicular, and this one will be, that's about right there, we'll call this one F parallel. Now, why did I do that? We certainly can agree, everybody can agree, that the sum of F perpendicular and F parallel is the same as F. So I can completely, legitimately replace F with F perpendicular and F parallel. Now, is F parallel, just thinking about this, is F parallel going to cause us any, is this going to cause us any rotation at all? No. The only component of F that's going to cause me rotation is the perpendicular component right here. So if I do the right hand rule, I do R cross F, right? So I do R cross F. Will this work? Oh yeah, so what I'd have to do is move sketch my drawing a little bit so that they're perpendicular to each other. So my R vector is going to be like this. And my green vector is going to be like this, so it looks a little bit more, they're tail to tail, so we'll call that F perpendicular. And if I do R cross F, let's do that. I don't know what I'm doing with colors here. This is what happens when I make my notes in black and white and I try to add colors. So if I go that way, my right finger is another wrist bust here, my right finger is going this direction, so the vector is going to be, the resultant vector is going to point down into there. So that's why I see the fletching on the arrow. This is going to be R cross F perpendicular. Right? I could have crossed it with the entire force, but that wouldn't change the area of the parallelogram at all. The only component of this force that provides, that contributes to the cross product is this perpendicular one here. So that is the kind of a primer on what the cross product is, right? But I've been promising for a long time that the whole point of using vectors is that it eliminates the trig, right? We replace the trigonometry with vectors by these clever definitions. The next video will include how to actually calculate the cross product, right, without using trig. So with that, I hope you got a little primer out of this, and you'll see me in the next video.